Section 5.2, the addition rule and complements. By the end of this lesson, you will be able to use the addition rule for disjoint events, use the general addition rule, and use the complement rule. Now, objective 1, we're going to be using the addition rule for disjoint events. Now, two events are disjoint if they have no outcomes in common. Another name for disjoint events is mutually exclusive events. We often draw pictures of events using Venn diagrams. These pictures represent events as circles enclosed in a rectangle. The rectangle represents the sample space, and each circle represents an event. So, for example, suppose we randomly select a chip from a bag where each chip in the bag is labeled 0 all the way to 9. We're going to let E represent the event, choose a number less than or equal to 2. And we're going to let F represent the event, choose a number greater than or equal to 8. And these events are disjoint, are shown in the figure. So you can see here, here's event E, and this represents choosing a number that's less than or equal to 2, so we have 0, 1, and 2. And event F is a number that's greater than or equal to 8, which is 8 and 9. The entire rectangle is the sample space, and the remaining numbers are in this sample space, meaning 3, 4, 5, and 6, and 7. So let's take a look at this. We want to find out if we want to find the probability of this event, meaning what is the event that event E, meaning how many numbers do we have in event E? Well, if we take a look at that, we can see that we have 1, 2, 3 in event E. So the number of outcomes in event E is 3. Now, how many numbers do we have total in the sample space? Well, in the total sample space, we know that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So therefore, it's 3 over 10. That's how many that are in a sample space. So 3 divided by 10 is going to give us 0.3. Now, if we want to find out what are the number of outcomes in F, meaning that, okay, so what are the numbers? What are the total numbers in event F? Well, we know that we have 2 numbers. So there's 2 numbers in event F, and then we're dividing it by the number in the sample space, which again we know is 10. So therefore, 2 over 10 gives us 0.2. Okay, now the next thing here says, okay, now what is the probability that we have a number in event E or a number in event F? That means how many do we have in both event E and F? So what that means is, okay, what numbers do we have in both? Well, if you noticed, we have 1, 2, 3 there and 1, 2. So when we add those together, that's going to give us 5. So 1, 2, 3, 4, 5, there's 5. And what is the number that's in the sample space? We know it's 10. So therefore, 5 divided by 10 is going to give us the decimal 0.5. Now, another way of doing this is we can take the probability of event E and adding the probability of event F. Well, the probability of event E gave us the following result, which was 0.3. And we saw that the probability of event F is 0.2. So if we add those together, it's going to give us 0.5. So this is a disjoint event, and we're adding the probabilities of E and F to get the following result, which is the same thing as the number of outcomes in E or F. Now, the addition rule for disjoint events. If E and F are disjoint or mutually exclusive events, then this is the definition. We would say that the probability of E or F is equal to the probability of E plus the probability of event F. Now, the addition rule for disjoint events can be extended to more than just 2 disjoint events. Okay, so let's say we had 3 events, E, F, and G. Each have no outcomes in common, and they are pairwise disjoint. Then we would say that the probability of event E or F or G or whatever other events that we would add to this would equal the probability of event E plus the probability of event F plus the probability of event G, and so on. So if we take a look at this here, again, here's the sample space, and we're going from 0 to 9, which means we still have 10 numbers in there. Now we have 3 events. Event E has 0, 1, and 2. Event G has 5 and 6. And event F has 8 and 9. And the sample space outside that is 3, 4, and 7. So there's 3 number of outcomes in event E. There's 2 outcomes in G and 2 outcomes in F. So, again, we saw earlier that how many outcomes do we have in event E? Well, we see that there are 3 outcomes in event E. And we're dividing it by the total number in the sample space, which is 10. And we end up getting 3 over 10, which is 0.3. Okay, the probability of event F. Okay, well, what do we know there? Well, we know that we have event F, and so how many numbers are in event F? We know that we have 2, and we're dividing it by the total number in the sample space, which is 10, so 2 divided by 10 gives us 0.2. Okay, now, what about event G? Well, what is the probability of event G? Well, we know that in event G, the number of outcomes are 1 and 2. So we have 2 over the total amount that's in the sample space, which is 10. So therefore, this is 2 divided by 10. Now, if we wanted to then find out what is the probability of E or F or G, well, that means the probability of event E plus the probability of event F plus the probability of event G, which equals 0.3 plus 0.2 plus 0.2 equals 0.7. So we're adding all of these up to get the probability of 0.7. Okay, now let's take a look at another example here. Okay, now example, Benford's law and addition rule for disjoint events. Now our number system consists of the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Now, because we do not write numbers such as 12 as 0, 1, 2, the first significant digit in any number must be 1 all the way to 9. Although we may think that each digit appears with equal frequency, so that each digit has a 1 out of 9 probability of being the first significant digit, this is not true. In 1881, Simon Newcomb discovered that first digits do not occur with equal frequency. The physicist Frank Benford discovered the same result in 1938. After studying a great deal of data, he assigned probabilities of occurrence for each of the first digits, as shown here in the table. The probability model is now known as Benford's law and plays a major role in identifying fraudulent data on tax returns and accounting books. So for part A, it says, verify that Benford's law is a probability model. Well, the first thing we need to do is we need to verify that each probability is between 0 and 1 inclusive, and then that the sum of all the probabilities equals 1. Well, first of all, here's the digit. Now look at the probabilities below. Now, if you look at each probability, they're all going to be in between 0 and 1 inclusive. So therefore, we know that it works for rule number 1. For rule number 2, we want to find the sum of all the probabilities. So if we add up all the probabilities from 0.31 all the way to 0.046, we get the number 1. So therefore, we can say that because rules 1 and 2 are satisfied, then this table represents a probability model. Okay, now the next question in part B says to use Benford's law to determine the probability that a randomly selected first digit is a 1 or 2. So the approach is to use the addition rule for disjoint events. If E and F are disjoint or mutually exclusive events, then we would say the following. We would say that the probability of E or F is equal to the probability of event E plus the probability of event F. Okay, so what we're looking for is the first digit is either a 1 or 2. So we're finding the probability of 1 or 2. So what that means is we want to find the probability of 1 plus the probability of 2. Well, if we look at our table here, we know that when the digit is 1, the probability of 1 is 0.301. So therefore, that's the probability of 1. And the probability of 2 is 0.176. Now, when we add those together, we get a probability of 0.477. Now, looking at that result, when we get that probability, we can round that to, let's say, 0.48. And if we write that as a fraction, it's going to be 48 out of 100. Okay, so down here it says if we looked at 100 numbers, we would expect about 48 of them to begin with a 1 or a 2. Okay, next, in part C, it says use Benford's law to determine the probability that a randomly selected first digit is at least 6. Okay, so we need to make sure that we understand what does it mean about at least. Well, the phrase at least means greater than or equal to. So at least means equal to 6 and then greater. So again, greater than or equal to, so that at least 6 means 6, 7, 8, or 9. So we're going to use the addition rule for disjoint events. So if E, F, and G, and so on, each have no outcomes in common, they are pairwise disjoint, then we would say that the probability of E, F, or G, or so on, is equal to the probability of E plus the probability of F plus the probability of G. Okay, so again, we're looking for the probability of at least 6, okay, which is equal to the probability of 6, or the probability of 7, or the probability of 8, or the probability of 9. So that means that we want to find, okay, the probability of 6 plus the probability of 7 plus the probability of 8 and then plus the probability of 9. So looking at our table, what is the probability of 6? Well, the probability of 6 is 0.067. Okay, then what's the probability of 7? Well, the probability of 7 is 0.058. Okay, and the probability of 8 is 0.051. And let me change that last color there for this one. The probability of 9 is the following. 0.046. So if we want to find the probability of at least, then we would add these together to give us 0.222. So if we round that to 0.22, well, that means the same thing as 22 over 100. So again, we would say that if we looked at 100 numbers, we would expect about 22 of them to begin with a 6, 7, 8, or 9. All right, let's take a look at another example. Okay, the example says that a deck of cards and the addition rule for disjoint events. Now suppose that a single card is selected from a standard 52 card deck, such as the one shown here. Now in part A, we want to compute the probability of the event E being drawing a king. So we want to find, okay, the event drawing a king. Now, because the outcomes are equally likely, and remember that equally likely means that an experiment has equally likely outcomes when each outcome has the same probability of occurring. We're going to use the classical method for computing the probabilities. That means that if an experiment has n equally likely outcomes, and if the number of ways an event E can occur is m, then the probability of E, or the probability of E is, the probability of E is equal to the number of ways E can occur, m, divided by the number of possible outcomes, n. So when we take a look at the standard deck of cards, we should see that we have 52. So that means that the sample space consists of 52 cards in the deck. So that means the number of possible outcomes is going to be 52. So when we want to find the probability of a king, which is the probability of event E, then we need to find out what is the number of kings that we can get from that deck of cards. Well, the standard deck of cards has 4 kings. That means that we have 1, 2, 3, 4 here. Okay, so therefore the number of that event E, meaning drawing a king, is 4. And we're dividing it by the number of possible outcomes in the deck of cards, which is 52. So if we take 4 and divide it by 52, then we would get 1 over 13. Now remember, we can convert that to a decimal if we wanted to. So if we wanted to do that, we can go in our calculator and then we can simplify by taking 1 and dividing it by 13, which gives us 0.0769. If we wanted to round that to 3 decimal places, then that would be 0.077. Now, if we rounded that again, then this would be 0.08. And so remember that the 8 is in the 100th place, so that means 8 out of 100. So that means out of 100 times, the probability of drawing a king is 8 times out of that 100. Okay. Next, in part B, it says, compute the probability of the event E, meaning the event E is drawing a king, or event F is drawing a queen, or event G, which is equal to drawing a jack. Now notice that the events are mutually exclusive, meaning that 2 events are disjoint or mutually exclusive if they have no outcomes in common. Now, because you cannot simultaneously draw a king and a queen at the same time, therefore, we're going to use the addition rule for disjoint events to compute the probability. Now, if E and F are disjoint or mutually exclusive events, then we said that the formula for that is the probability of E or F is equal to the probability of E plus the probability of F. And if there are more than one event, then we would have probability of event E plus the probability of event F plus the probability of event G. Now, in our question, okay, we know that we have drawing a king, drawing a queen, or drawing a jack. So in our standard deck of cards, okay, we know that we have 4 kings. So 1, 2, 3, 4 kings. Okay. We also know that we have 4 queens. That's 1, 2, 3, 4 queens. And we also have 4 jacks. So we have 1, 2, 3, 4 jacks. Okay. Now again, because the events E, F, and G are mutually exclusive, we're going to use the addition rule for disjoint events extending to 2 or more disjoint events. So the probability of a king or a queen or a jack is equal to the probability of event E or the probability of event F or the probability of event G. So we know that the probability of event E is 4 kings. So that's 4 out of the total numbers that's in the deck, and we know that that's 52. Okay, the probability of 4 queens, 4 queens is 4 over the total in the deck is 52. Okay, and then the probability of 4 jacks is 4 out of the total amount of the outcomes is 52. So now we have 4 over 52 plus 4 over 52 plus 4 over 52. If we add these fractions, we get 12 over 52. And then we want to reduce that fraction. So when we reduce that fraction, we're going to divide both the numerator and denominator by 4. So then we get 3 over 13. Now, if we want to convert this into a decimal, we can take 3 and divide that by 13. And then let's round up to 3 decimal places, which gives us 0.231. So that gives us the probability of 0.231. Okay. Now, if we wanted to round that to 2 decimal places, then we would get 0.23. And if we converted that to a fraction, we would get 23 over 100. So what does that mean? That means that the probability of selecting a king or a queen or a jack from a deck of cards out of 100, we would expect that 23 out of the 100 would be the possibility of that probability.